All right, we are at number 14, and I'm sorry that I've been listening to a couple of my other videos, which I don't generally listen to them after I've recorded them. I just post them and I move on. It sounds, I don't know, kind of like staticky or something on the first two videos. I did a test right before this to make sure that this one didn't sound staticky, so hopefully it doesn't. I don't know. But I mean, if it does, it's not really much I can do other than keep going with the video. All right, well, we are in number 14. Oh my goodness, there goes my air conditioner. Pause. Yes, no doubt that air conditioner makes it harder to hear, I'm sure. I haven't gotten to that part in any of my other videos just yet. Usually I have it off, but every once in a while it's on. Anyways, now it's off. Okay. Calculate and interpret probabilities for probability distributions. GE manufactures a decorative clear 60-watt light bulb that it advertises will last 1,500 hours. Suppose the lifetimes of the bulbs are approximately normally distributed with a mean of 1,550 hours and a standard deviation of 57 hours. What percentage of the light bulbs will last less than the advertised time? Okay, so some keywords here. First of all, what percentage? My answer should be a percent. Okay. Says normally distributed. Less than. Those are some of my keywords that I want to focus on. So let's see here. Let's look for all the numbers, right? Usually that's what I do. I go through and I try to find all my numbers so I can start labeling them. The first number I see is 60 because it says it's a clear 60-watt light bulb. All right, and this number is just describing what type of light bulb it is. So this is not an important calculating type number. It's just descriptive, telling you about the light bulb. So that 60, that doesn't play a role in our problem. But it says that this bulb, it advertises will last 1,500 hours. Okay, that's the advertised time. And so let's see here. I'm going to go ahead and write here, this is advertised time. That's going to be X is 1,500. Maybe I want to do a different color. I don't know. I'll do that one in black. Okay. Suppose the lifetime of the bulbs are approximately normally distributed with a mean of 1,550 hours and a standard deviation 57 hours. Okay. So the mean, okay, we are talking about, this is our population, right? Normally distributed. So they're saying that the mean here is 1,550 hours. Our standard deviation, sigma, is 57 hours. And X here, 1,500. We want to know the percentage or probability or, right? Remember when I said you're looking for some keywords that say find the probability, find the proportion, find the percentage, find, things like that in terms of the normal distribution, then that means that you are going to be using the normal CDF. Okay, so I'm just going to go ahead and write here, we're looking for the probability that our X is less than the advertised time. So X is less than 1,500. Okay, so let me show you our picture, right? So we need to draw a picture. A bell curve, normal distribution, right? What number goes in the middle? I know you're answering me right now. It says mean is 1,550. Of course, that's in the middle, right? So let me go ahead and just put that there, 1,550. Okay, and then we are wanting to know when it's less than 1,500. So let's pick a side, right? Where's 1,500 on a number line in comparison to 1,550? Well, here's 1,550, so 1,500 is less than that. So we're going to put that line here, which I probably should have given a little more space. Let me give myself a little more space here. Put 1,500 there. Okay, and I want to know if it's less than this, right? So shade this area here. Well, I usually use a pencil to shade because the pencil shade's a lot prettier. Let's use the pencil, shall we? It just shades so much nicer. You guys know I love pencils. Okay. All right, so we're looking at this area here. So we want to know the probability. Now, what is this interval, right? If this goes on forever, right? This is a number line, right? This is negative infinity up to 1500, right? This is my lower bound. This is my upper bound. So when we're talking about doing, I said we're going to use the normal CDF because normal CDF is what you use in order to find an area, probability, proportion, percentage, all of those things wrapped up into one. Those are all the same here. And it's this space that I shaded in purple. If I want to find that, I need to use a normal CDF. So normal CDF. Remember, we only use CDF because it's an interval. We don't ever use the PDFs. We're going to put your lower bound, which is negative infinity, or in other words, negative 1e99 for the calculator purposes. Upper bound, 1500. Oh, I didn't leave enough space. Hold on. I'm going to need to put some more space here. Okay, I'm going to be real with you. It's been like 3 days since I started this. I don't really remember where I left off, but I think what I was talking about was the lower bound and the upper bound. And pretty sure that's the last thing I mentioned. And I remember saying something about liking to shade with pencil because it's so much better on here. So anyways, we have an interval here where we've shaded, right? And this is up to 1500, but we know that it goes out to negative infinity because as you decrease on a number line, that's the direction you're headed, right? It's out to negative infinity. Well, okay, sorry. When an email comes in, it comes in like 6 places and then beeps everywhere. All right. So let me do that. Okay. So, we are, now looking at, we've got a lower bound and an upper bound. Now, when we do, I remember now, I had erased because I didn't have enough space. Normal CDF, I'm going to do it way down here so I have enough space. And I know I explained why we do normal CDF because of the fact that this is a normal distribution. And we don't ever use the PDF because we're not looking for any specific value. We are looking for a range of values. So when we put this in here, for the lower bound, instead of negative infinity, we need to do negative 1e99. That's just for the calculator to tell it what negative infinity is. And then our upper bound is the 1500. Then we do mean and standard deviation. Our mean is 1550. Oh, I'll color code. 1550. And then our standard deviation is 57. There we go. And this is what we're going to be putting into our calculator. So we've got lower bound, upper bound, mean, and standard deviation. And I will show you where to find that on your calculator. So let me pull up my calculator here. And okay, so for normal CDF, we're going to go under the distribution. So second vars, and it's the second one right here, number 2. And it says normal CDF, right? So hit that. Usually it defaults to your lower bound being negative 1e99, which is nice for us because it's already there, but I'm going to go ahead and clear that and show you how to type that in if it's not there. Or if you have to do 1e99 for the upper one, right? So we'll use the negative that's here at the bottom in parentheses, and then 1. That E part, it's actually this double E right here in blue that you see right above the comma. So if you hit second and then the comma button, it'll put that E for the exponent for scientific notation. And then 99. Your upper bound we said was 1500. Then our mean was 1550. And our standard deviation was 57. And we will hit paste, enter. And here we go. We will round this to 4 decimal places, but actually I think our problem asked for a percentage, right? I'm going to still round this to 4 decimal places, 0.1902. Okay, so 0.1902. And then if we write that as a percentage, that will be 19.02%. It didn't ask us how to round or tell us how to round it, but this is like the only time you convert to a percentage when it specifically says what percentage. Okay. All right, from these light bulbs, GE quality control randomly selects 10 bulbs. What is the probability that the mean lifetime for the 10 bulbs will be at most 1,500 hours, the advertised time? Okay, so a few things that you might notice here is that this is talking about, and this is really key here, the mean lifetime. Okay, so when you see the, the mean lifetime for the 10 bulbs. Sorry, let me just go ahead and highlight the whole thing. Mean lifetime for the 10 bulbs. Okay, this is the mean lifetime of a group of light bulbs. Okay, so when you're doing the mean of a group, you should be going, hey, I think that was that like chapter 8 stuff maybe, or maybe it wasn't chapter 8. But when we did mean of a group, and I'm just going to write that out here, mean of a group. The thing is, we had to consider how we would find our standard deviation, right, when we plug it into normal CDF. And so I'm going to talk about that. I'll give you that formula here in a second. On your formula sheet here, under chapters 7 and 8, oh yes, this was chapter 8, we had to find the standard deviation of the sampling distribution, and or of the sample mean, right? So we have the way to find that as a formula given. So let me write down what we already know. So we had the mean was 1550, right? The standard deviation was 57. This time our x here is 1500. And what else did they give us? They gave us another number, right? Oh, I already, spoiler alert, I wrote that as I said that. Okay. They gave us another number, right? They gave us this one, the 10 bulbs, right? That's your n. So n equals 10. Okay. So that's something new, right? If you're given an n and it's asking you for, normal CDF type stuff and things like that, that should be an indicator to you that you're going to need to use this, the central limit theorem, finding the mean and the standard deviation for your sampling distributions. So on your formula sheet, it tells you that your mu sub x bar, so the mean of your sample means, so you've got, the mean of your sample mean. Okay, this is just equal to the mean here. Okay, so that one stays the same. And then for the standard deviation, this is where we did sigma, so divided by n. Okay, that maybe hopefully looks a little familiar to you. Again, this is only when you're doing like normal CDF for like a group of things, right? That's why I say mean of a group. So when you see that. Okay, so we've got this, it's actually going to be the same picture as above, so I don't think I should really redraw it, I think. It says at most 1,500, right? So at most 1,500, at most. That's the same as the picture we have up here in part A. So I'm going to go ahead and just leave that picture there and not redraw it. It's kind of unnecessary. And so our normal CDF is going to look the same way. We have that same exact lower bound, upper bound, right? And so our lower bound is negative 1e99. This is calculator, of course, 1,500. Okay, the question is, what do I put for mean here? Well, remember we said mu of x bar is the same, or mu sub x bar is the same as mu. So in this case, still 1,550. This is the part that changes, right? That the standard deviation, so sigma sub x bar, is equal to sigma divided by n. So it's going to be 57. Oh, wait, hold on. Whoa, hold on. I made a mistake. Square root of n. My apologies. That was a big mistake. That should have been square root of n. I realized it. Luckily, figured that out, and that's an easy thing to add on. Okay, don't forget your square root on the n. Again, it is on the formula sheet. I don't know. I looked right at it and still didn't write it correctly. Okay, so let's try this again now. 57 divided by the square root of 10. There we go. So when you go to plug this in your calculator, and even if that's a perfect square, I just recommend typing it the way that you see it here. So let me show you, again, how we do that. So you'll go second vars, it's the second one, Okay, all of these are the same except here, sigma, right? And we said 57 divided by the square root of 10. So 57 divided by square root of 10. And just type it in that way so it's perfect. It's exact, right? It's exactly the number. We're not putting any kind of estimated value there. We're just putting the exact answer because it'll calculate that for you. No problem. So just leave it there like that. Okay, hit enter and you get 0.0028. 0.0028. Okay. There we go. So this is your probability, right? Didn't ask for a percentage this time. It just said what is the probability. So we found it. All right. Next problem here we've got. Oh, I tell you what. Every time it does that to me, I don't know why. According to the U.S. National Center for Health Statistics, there is a 98% chance that a 20-year-old male will survive to the age of 30. Seems like you'd want that percentage to be just even a little higher than 98%, but okay. In a random sample of 250 20-year-old males, find the probability that at least 245 survive to the age of 30. Would it be unusual for at least 245 to survive to the age of 30? All right. Well, let's see here. This seems kind of like here's the question everybody always asks me. How do you know when to do like normal and binomial and all that kind of stuff, right? And I said for, normal probabilities, I mean, it should say something about being normally distributed generally in the problem, right? It'll say it's normally distributed. For binomial type stuff, what I'm really looking for is this like a success failure type situation, like passing and failing, yes or no, heads or tails, survive or die, those kinds of things that are like binomial. Because, two different outcomes, right? Now, of course, we know there's other requirements for the binomial stuff. There has to be a fixed number of trials. They're independent. Probability of success is remains constant on a single trial. So, yeah, there's several things, right? So when I read this, though, and I'm seeing that there's a 98% chance that a 20-year-old male will survive to the age of 30. Okay, well then that means there's a 2% chance that he won't, right? And to me, I'm hearing that and I'm thinking, oh, okay, well you either survive or you die. That seems like only two outcomes, right? I mean, there's nothing else. And you've got a percentage there, a probability for that. The probability of survival is constant. It's 0.98. The probability of death will be 0.02. So that seems okay. I've got a fixed number of trials. I got 250 people. So are they independent? Well, let's see, 250, if I divide that by 0.05, I get 5,000. That seems like that's way less than the whole population of 20-year-old males. So to me, this says it's binomial. I mean, it meets all the requirements, right? So I'm going to write out here that this is binomial. Okay. And so let's write down all the things that we need to know. So several things, like we need to know n. We need to know p. I don't know if we necessarily need to know q. I mean, we don't put that into the problem, right? We need to know our kind of our x and stuff. So let's see. It says random sample of 250. All right, so my n is going to be 250. I got a better idea. Let me do it this way. N equals 250. And then let's see here, p. So this is the probability of success. Now, once again, I want to say that success does not necessarily mean that it's a good thing. I mean, I know in everyday language you hear success and that's a good thing. But in statistics, success just means that this is the stuff we were measuring, right? That did it meet what we were looking at measuring, right? So if we're talking about measuring survival right? Then that would be considered success. Now, if we were looking at, probability of people, dying or whatever, death, well, then death would be considered a success. I know that sounds terrible because you're like, it's not a success if someone dies, but you have to take that out of your mind when you're thinking about this. You're saying success only means that it is what we were looking at. Like, did it do what we were asking about, right? Did this person survive? That's a success, because that's what we're trying to measure here. Find the probability that at least 245 survive. So survival is considered a success in this question, okay? So it's what we're counting. All right, so our probability here of survival is that 0.98. 98% chance that he will survive, okay? And then, let's see, the other thing we're looking at here is like kind of our inequality, or an equality, whatever it looks at. Now it says at least. That means it's an inequality. At least 245 survive. So this is the probability that, okay, what does at least 245 mean? It means at the very lowest, 245 will survive. So either 245, 246, 247, 248, 249, 250, right? That any of those would be what we're looking for. So at least 245 means that X is greater than or equal to 245. Okay, that's that part. Now, in your calculator, first of all, since this is an inequality, are we going to do binom PDF or binom CDF? Well, PDF is used for only one exact value, a specific value. When you're doing an inequality like this, you are going to use the binom CDF, okay? So use binom CDF. Okay, you only use PDF if it says exactly, okay? Only for the word exactly. If it says exactly 245, then you'd use binom PDF. But because it says at least 245, we're going to use binom CDF. Here's the downside. In order to use binom CDF, remember, it has to be in this form. X less than or equal to some number here. All right. And so if we have it as greater than or equal to, then we're going to have to rewrite it using the complement, right? So if we're talking about discrete cases, which we are, then when we say greater than or equal to 245, another way to write that would be, so greater than or equal to 245, you could say greater than 244, right? Wouldn't that be considered the same? Yeah, right? Greater than 244 in a discrete scenario means, okay, then 245 up to 250 in this case. Greater than or equal to 245 means 245 up to 250. So these are the same. And you might be wondering, well, why did she rewrite it that way? And I'll show you why. Because it comes out in terms of the complement. When we do the complement, if you remember that the complement of any inequality is you flip the inequality and you either add or take away the line that's there, right? So depending on if there's a line. Well, I want it to be in this form, right? I want it to be in less than or equal to. So what I want is for when I do the complement for it to be less than or equal to. So if I made this greater than here, when I flip it, doing the complement, it will now be less than or equal to. Now you could do it either way you want. I mean, you could flip it first, take away the line, and then change it from there. I just find it's a little easier to maybe start it that way. Okay, so I started it this way. Okay, so now in terms of the complement. So when we do the complement, the only way you can flip this is by doing this. 1 minus, okay? Everybody forgets that 1 minus, but we're doing 1 minus the probability, and now we're going to take the complement. This is where X is now less than or equal to 244, okay? We flipped it, made it 244. Okay, I'm sorry, flipped it and added the line. That's what I wanted to say. 244 was already there. All right, now we are ready to put this in the calculator using binom CDF because we have N, we have P, this is now our X here, right? The maximum X value. That's what we're going to be putting in the calculator. So when I write it though, 1 minus, it's going to be binom CDF, and it goes in order NPX, right? So N is 250. P is 0.98. And then my X value here, which I'm going to go ahead and, actually in your formula sheet it says max X. That's this guy right there. That's going to go here. Okay. You only fill that number in once you've got it in the correct format, which is, like I said, less than or equal to. Okay. It has to be that. Okay. So now when I go to plug this in, here's a word of caution. Whenever you realize you're going to have to do your complement, just go ahead and pick up your calculator and type in 1 minus, because inevitably what always seems to happen is that you look at this and you know you have to do the complement and you do it and you write it all down and still you go to your calculator and you forget the 1 minus. I do it all the time. I'm telling you, I always do it. And so I really just want you guys to be successful on this problem. I don't want you to miss this because you forgot the 1 minus. So anyways, so what I would do is say, oh, I know I'm going to need to use a complement. Oh, pause. Let me grab my calculator. I'm going to go ahead and put 1 minus just so I don't forget. And then I'm going to come back. I'm going to keep working my problem. And then I'm going to go, okay, so when I pick up my calculator, I already see the 1 minus there. And I'm like, oh yeah, that's right, 1 minus, because I already wrote that down. Okay, so then we're going to do 1 minus. So second vars. Remember the binom stuff was like way at the bottom? And we want binom CDF, right? Because we're not doing an exact value and we're doing an inequality. So we're going to choose option B there. Trials is your N. So in this case, your N was 250. And your P was 0.98. And the X value, that was the thing that I wrote there in orange. That's your 244. Okay, and then you're going to paste. Okay, so you notice the 1 minus is there. Okay. All right, we get 0.61596. And, okay, so that means if I'm rounding this 6 here bumps the 9 up, which then bumps this 5 up. So it's going to be 0.6160. So let me come back. 0.6160. Okay, now there's another question in here. This is the probability, right? The other question says, would it be unusual for at least 245 to survive to the age of 30? And so remember when we're comparing for this type of problem to see if it's unusual, then we would, well, let's see, I think, and we would use the mu plus or minus the 2 sigma, right, to see if it's in between. So, I mean, I look at that and I say 61%, and I'm thinking, it doesn't seem like it. I'm sorry, I'm just debating because, and when I've done this in the past, I've always done it, actually as, I just compare it to the 0.05. But I actually think we're supposed to use the, maybe I have a different problem where we use the mean. Oh, I do have another one where it says, is it unusual by mean and standard deviation? I would say on this one, let's just go ahead and we'll compare it to the 0.05 for right now. 0.6160 this is definitely greater than 0.05. It's a lot more than 5%. So I think we're safe. We're going to say this is not unusual here. Okay. If I was going to compare, oh, I know why. Okay, hold on. Nope. Sorry. I understand now. I know why. On the other, okay, so on this one here, we are just looking at the probability and determining that. On the other one that I'm thinking of, which I think is on the next page, it's asking, would it be unusual for this many people? And it gives like a specific number. And then you calculate the mean and standard deviation and compare it. So, yeah, I think we're good on this one. Okay. By the way, if you wanted to just kind of test it out, I mean, I don't think it's going to tell you what you really want. I guess, you know what? Just let me, I'm going to pause and I'm just going to calculate some stuff and then I'll maybe come right back. Okay, so yeah, no, my first instinct was right doing this, checking the greater than 0.05. I think I was just thinking about something else. When I started looking at this, I was like, no, this one doesn't really make sense. So, to do that. So anyways, we're good here. All right, part C. A particular cicada species has a mean lifespan of over 16 years with a standard deviation of 1.2 years. A random sample of 50 of these, herbivorous bugs. Is it herbivorous or herbivorous? I don't know. I would say herbivorous, but I don't know. I mean, I say herbs. I don't say herbs, but, unless I'm joking. But anyways, herbivorous bugs was kept in a museum, and they had a mean lifespan of 17 years. Find the probability that a random sample of this cicada species would have a mean lifespan of 17 or more years had something unusual occurred. Okay, this one sounds a lot like the one 2 questions ago where it talked about the mean, lifetime of a light bulb, right? They had a group of things. So let's look at this one here. So it says we've got mean lifespan of 17 or more years. So random sample, particular cicada has a mean lifespan of 16 years. Okay, so let me write this down. This is the population mean, because that's just saying in general for that cicada species, this is their mean lifespan. Okay, standard deviation 1.2. A random sample of 50. Okay, so random sample of 50. This is n equals 50, right? And then Beaver's bugs was kept in a museum. Okay, so the ones that so they have this random sample that were kept in a museum, and their mean lifespan was 17 years. Then it says find the probability that a random sample of the cicada species would have a mean lifespan of 17 or more years. So this means probability of 17 or more years means x greater than or equal to 17, right? 17 or more greater than or equal to, okay. Has something unusual occurred here. All right, so the question is, how do I go about doing this problem, right? So again, I'm given a mean, a standard deviation, and n. I have some kind of a probability situation here. If I went up here, it seems kind of like this first one here, where I am doing like the graph and shading and all this kind of stuff, has all the same information, right? And then on part B, though, this was talking about a mean of a group when I got the n, right? So I think it's kind of like these up here, right? So I think I'm going to draw a picture. Sounds like a normal probability type problem. Now, it doesn't say normally distributed in here, and I think generally your problem will say that it's normally distributed, but I mean, it doesn't make sense to do binomial here. You're not given any kind of probability already, which is what you would be given if you're doing a binomial type problem, right? If you're looking for a probability, this is more of a normal CDF kind of situation. Okay, so let's draw a picture. There we go. It says the mean, 16 is right there in the middle. And the question says they would have a mean lifespan of 17 or more years. All right. Let me go to my pencil. And I'm going to go, I will shade this in purple, I guess. So 17 or more. There's 17. Should have done that in pen. Okay, here's 17. 17 or more when you shade this direction. There we go. Okay, 17 or more. So how would I write that as an interval, right? So as we continue on to the right, forever, this goes all the way out to positive infinity. Yeah? So there's your interval there, right? This is your lower bound now. This is your upper bound. So now when I do my normal CDF, okay, this is what I need. Normal CDF. And you start with your lower bound, which is 17. Your upper bound is going to be 1E99. Okay, and because we are doing the mean of a group, let me write this over here. Mean of a group, right? It's the group of 50 that live in this museum, right? So there's a group of 50, which means we have this n. We have to deal with that. So we've got our mean, which is 16. Remember, we said that's going to be the same each time. But then for this one here, so sorry, let me put here mean, and then sigma of x bar equals sigma over the square root of n. I didn't forget the square root this time. Okay, so now my sigma is 1.2 divided by the square root of 50. Okay. So when I put this in my calculator, and since I've already demonstrated, I will not demonstrate it, but I will go ahead and write down the answer here, which is what you're thinking. Oh, girl did something wrong. She put 1.9, and this is a probability, right? Probabilities aren't 1.9. You're right. They can't be more than 1, but I will tell you that now, actually, it's 1.9 times 10 to the negative 9th. There we go. Okay, so if I write this as a decimal, let's say this is going to, like without the scientific notation, like a standard form, this is going to be a decimal with 1, 2, 3, 4, 5, 6, 7, 8 zeros and a 1, 9. So the question is this less than or greater than 0.05? Because it says, has something unusual occurred here? I think on my answer key, I have it rounded to, instead of 1, 9, I put a 2 there. That's all right. So yeah, has something unusual occurred? I would say so. I mean, I'm sorry, but this probability is basically 0. I mean, let's be real here. This is like almost impossible, right? It's not quite impossible because, I mean, it's not exactly 0. So, I mean, it could happen, but it is extremely unusual. I mean, this is by far way less. Was that 4, 5, 6, 7, 8? This is way less than 0.05, like way less. So, yes, something very unusual has occurred here. Occurred, does it have 2 C's? It does. And 2 R's. Okay. So we've answered both of those questions. All right, man, we're done with page 9. All right, page 10. Use mean and standard deviation to assess if an outcome is unusual or not. This is where, so this is the problem I was thinking of. This is where we're going to use the mean and standard deviation. All right, it says 41% of U.S. women consider reading as their favorite pleasure time activity. Okay, so when I read this question, I don't know about you, but it feels awkward when I read it. It says, I almost actually changed it from the review, and then I decided not to because I just thought it was kind of funny. And it makes me giggle. So 41% of U.S. women consider reading as their favorite activity. I'm just going to say activity. Okay. In a random sample of 34 women, would it be unusual by mean and standard deviation to find that 20 women consider reading as their favorite activity? Sorry. Okay. So let's write down what we know here. Okay, so we're given some stuff. First of all, like what are we looking at here? Is this like normal or is this binomial? Like what do we think? So I'm seeing that I'm given a percentage, right? So I would say that makes me lean a little more towards that this is binomial. So let's see here. It says 41% of U.S. women consider reading as their favorite activity, which means that 59% of them would say that it's not their favorite activity. So that sounds like a 2 outcome type of thing, right? So binomial, remember 2 outcomes. What was the other stuff that were requirements when we were talking about binomial? It was that there had to be like a fixed number of trials, right? It says a random sample of 34 women. That would be a fixed number of trials. Is the probability of success on a single trial remaining constant? Yeah, because that's our given percentage there, so that's going to stay the same. And then are the trials independent, right? So if we're talking about Was it just U.S. women? Okay, I'm going to go with 34 is, yeah, definitely less than 5% of the entire population of U.S. women. Let's see, 34 divided by 0.05 is 680. Yeah, it's way less than the whole population of U.S. women. I mean, gosh, what do we have, like 330 million people in the U.S.? And if you just consider, let's say half of that is women, that's 165 million. I think 680 is substantially less than that. So I think we're good. Okay, so yeah, this meets all the binomial requirements. So this is binomial. Okay, and so let's write down what we know. First thing that we see here, actually, I want to keep my colors consistent. Okay, let me do this. So random sample of 34 women. So N is going to be my 34. P is equal to, remember that P is the probability of success, right? What we're trying to measure here is people that consider reading as their favorite activity would be considered a success, right? So 41% of women consider reading as their favorite activity. Then 0.41 would be the probability of success. Okay, so that's just what we're trying to measure. So 41% of U.S. women. Okay. So then the last part says we are looking at to find that, would it be unusual to find that 20 women consider reading as their activity? Okay, so let me go ahead and I'm just going to write, I'm going to call that, I'll call that X. No, I don't really want to call that X. Let me call that something else. We're just going to say, we're just going to leave that number there in a blue box and just leave it alone. One thing I do want to calculate, though, is Q, because we will need that to find the mean and standard deviation. Remember that Q is found by doing 1 minus P. So 1 minus 0.41 would be 0.59. And so we need to find the mean and the standard deviation of a binomial distribution. Well, on your formula sheet, it tells you that the mean of, this is like the easiest mean to calculate. The mean is going to be N times P, and the standard deviation is going to be the square root of N times P times Q. That's why we need a Q. All right, so mu, N times P. All right, so let's see here. Mu is going to equal 34 times 0.41. And 34 times 0.41 is 13.94. I'm just going to round it to 2 decimal places, because why not? I mean, really, I only needed to round it to 1, so maybe I should just round it to 1. I'll do that. We'll say 0.9. Okay? And because remember, when we do mean and standard deviation, we always round to 1 more decimal place than what our data was. And here we're talking about number of women. So our data is women. I guess I should have called that X, huh? Yeah, okay. All right, so let's look at standard deviation now. I'm going to put that here. Standard deviation is the square root of N times P times Q, 0.59. Okay, so 34 times 0.41 times 0.59 is equal, so, and then you take the square root of that, right? So square root of that is going to be 2.87 or 2.9. Okay, so here's our mean and our standard deviation. So if we want to know if it's unusual for 20 women to consider reading as their favorite pleasure time activity, then we're going to do mu minus 2 sigma. And we're going to do mu plus 2 sigma. And then, because it says by mean and standard deviation, right? So what that means is I'm going to calculate whether or not it's within 2 standard deviations or outside of 2 standard deviations. So we said that within 2 standard deviations should be like 95% of your data, right? And then outside of that would be 5% of your data. And so if it's outside of these, 2 standard deviations, then that means it's unusual. You know, whether it's less or more, either way, both of those would be considered unusual. If it's in the middle, just like with our lower and upper fences and things like that, if it's in between, then it is considered usual, not unusual. So let's calculate these. So mean 13.9 minus 2 times 2.9. Sorry, I have to actually, because I rounded it different from my answer key. So I just gotta make sure I get them right here. So this is going to be 8.1. And then if I do 13.9 plus 2 times 2.9, then I get 19.7. Okay, so the question is, so anything in between 8.1 and 19.7 is considered usual, right? On the outside of that would be unusual. So where does 20 fall? That's the real question, right? We've got a number line here, so you consider this as a number line. Yeah, 8.1 over here, you've got 19.7 over here. So let me just draw this. Let's pretend, here's our number line. Okay, where does 20 fall? Okay, you're right, 20 is right here, just on the outside. So 20 would be considered unusual. It's just over that, you know, 2 standard deviation mark. So we would say, when the question says, in a random sample, would it be unusual? Yes, it would be unusual for 20 women to consider reading as their favorite pleasure time activity. Wow. Okay. So there you go. There's that one. All right. 16. Determine z-scores. Okay, so let's see here. A carpenter measures his work carefully, but his measurements are subject to some naturally occurring error. If his measurements on average are off by 1/10 of a centimeter with a standard deviation of 9/100ths of a centimeter, find the z-score for a measurement that had an error of 1/4 of a centimeter. Interpret this z-score. I said 1/4, 25/100ths of a centimeter, which would be a fourth of a centimeter. I don't know. Anyways, I didn't like reading that as 25/100ths, but okay. Anyways, interpret the z-score. All right, so let's write down what we know. It gave us some stuff here. So I'll start with red. I come up here. If his measurements on average are off by, okay, it says on average, they're off by 0.1 centimeter. That number here is my mean, because it says on average. This is what they're off by. I guess I don't need the centimeter. I'm going to leave the centimeter part off. Okay, then the next thing I see, I'll go ahead and use orange. Standard deviation. So sigma 0.09. Okay, and it says that, so these numbers here, let me just I'm going to underline that for a minute, but let me just come back here when it says the carpenter measures his work carefully, but his measurements are subject to some naturally occurring errors. So what we're measuring here is the error, okay? So we're saying that the mean error that he has is 0.1 centimeters. That's the mean error. And then the standard deviation error is 0.09 centimeters. So now it says find the z-score for a measurement that had an error. So this is like your x, okay, of 0.25 centimeters. Remember, x is just your data point. And then interpret the z-score. So if you look on your formula sheet, there is actually in 2 places the formula for finding a z-score. It's on chapter 7 and 8. It's also under chapter 3. It's under chapter 3. It's the same formula. So on your formula sheet, it says z equals x minus mu divided by standard deviation. Now, I generally, when I write it, I don't put the parentheses, but I should warn you that on your formula sheet, it has them, and I think that's a great idea. Here's why. If you don't put parentheses when you plug it in your calculator, you'll get it wrong, right? So if you want to do it all in one step, just, like I said, put your parentheses. Okay, so let's plug all this in. Z equals 0.25 minus 0.1 divided by 0.09. Okay. Oh, parentheses. Okay. So when you type all that in, your z-score is 1.67. Remember, z-scores, we round to 2 decimal places. So 1.67. Okay. So how do we interpret this? So remember that we're saying that our x is representing the amount of error that you have, right? So when we're saying that for, okay, an error of, oh, I think I might need to fix my answer key. I just realized. But it's an error of 0.25 centimeters would have, is 1.67 standard deviations above the mean. So, that's what it is, right? And I mean, that makes sense because 0.25 is above 0.1. That's the average centimeters. So we would say an error of 0.25 centimeters is 1.67 standard deviations above the mean. Now, if it was a negative, I would, first of all, I'd be questioning that if it was negative because 0.25 is bigger than 0.1. But let's say, for example, we were asked to find a z-score for a measurement that had an error of 0.05, for example. Let's say 0.05. Well, then we'd get a negative z-score because 0.05 is less than 0.1, right? So you get a negative z-score. When you would interpret that, you would say an error of 0.05 centimeters is whatever that number is, still is going to be positive, but you say standard deviations below the mean. Okay, so this number here is always going to be positive. And then either if this z-score is positive, we say above. If the z-score is negative, we would say below. That would be the only difference, okay? This part right here would stay the same, the 1.67. That part would stay the same. The only thing that changes is the word above or below. Okay, so if it's negative, it's below the mean, right? Okay, so I'm gonna pause for just a brief moment to double check my answer key and make sure that it's correct. Good news, it was correct. I just had it written wrong somewhere else. So we're good. Okay. Assuming the carpenter's measurement errors are normally distributed, find the measurement error that separates the largest 10% of errors. Okay, so I see the words normally distributed, and that should kind of guide me to the fact that I maybe want to draw a normal distribution, like a bell curve, right? So I think that's what I'm going to do. I'm going to go ahead and draw a bell curve here. There we go. And right here's my mean. So my mean was 0.1. And it said, find the measurement error. Okay, the measurement error, that's my x. That's what I'm looking for, right? So let me come here. And it says the largest 10% of errors. Okay, well, what's the largest 10% of errors? Well, that means the top 10%, right? Well, top 10% is going to be up here on the right side. So what I'm looking for is for that area. Let me close this here. That area is going to be 0.10. That's 10%, right? and I'm looking for this value x right here. That's the number I want. So if we're talking about the largest 10% of errors, I want to know this number x, right? It should be more than 0.1. So when you give your answer, it should be more than 0.1. It should not be less. That wouldn't make any sense. Just basically, you're looking at your picture, right? Well, if I am going to use, like if I need to find this number x, this is where we use inverse norm, okay? Inverse norm is used for finding x values, okay? So we're going to say inverse norm. Okay, now here's the problem, because for this we always need to have area to the left, right? If I'm shading the largest 10%, then what does that tell me about the area to the left here? Okay, oops. The area to the left, this whole area, what is this? This equals, this equals 0.9, right? 90% to the left. If 10% are above or to the right, 90% are below or to the left, right? So when I'm putting this in my calculator, I'm going to be putting in area to the left of the number that I want, which is 90%. Okay, so inverse norm, area to the left, then you have mean and standard deviation, which we have in the previous problem here. It's 0.1, and then 0.09. Okay, now I do want to point out that I have a 0.1 up here for the mean, and then I have 0.10 here. Those are not related. So I know they're the same color, so I think I'm going to actually go real quick and just change my color coding just so that I want to avoid those confusions. Oh no. Oh no. Okay, let me try this again. Dang it. Okay, well, all right. Let me just redraw that part. All right, let's try this again. There we go. All right, so fix that shading. Okay. All right. Now we're good. Okay, so yes, I did want to point out that this 0.1 that I have over here is actually the 0.1. I'll color code those so that we have consistencies here. There we go. All right, now this makes sense. So now we can see where everything comes from, right? Because I want to make sure that that's clear, that the 0.9 is the area to the left. The this is, area to the left. This is the mean. This is the standard deviation. So now when we put this in the calculator, so let me show you where to go to do that. All right, so inverse norm, we're going to go to that second vars, and it's number 3 here, inverse norm. The area to the left was 0.9. My mean was 0.1. And my standard deviation was 0.09. And when I hit paste, oh my gosh, periods and or decimals and commas all over the place. Hit enter. I get 0.2153. But I guess for an x value, I think we'll go ahead and go with maybe 2 decimal places, because that's all that they went with on their problem. So just to, maybe I'll do 3 to be on the safe side. I'll just go ahead and do 3. 0.215. Okay. All right, so 0.215. Now remember that this here, this is our largest 10% of it. That's the measurement, right? So we need to have units on this. This is 0.215 centimeters. Okay. Estimate necessary sample sizes. Let me check my time here. Getting kind of long. I may have to end this video at this page and then mess up my 4-page thing. Okay, estimate necessary sample sizes. An urban economist wishes to estimate the proportion of Americans who own their home. What sample size should be used if he wishes to estimate within 3% with 92% confidence? Okay, when you're asked to, it'll say what sample size, right? That's your key word, your key phrase. What sample size or what size sample? That right there, you're going, oh yeah, there's a formula for that. You're right, there is. So you go on your formula sheet, you'll see under chapters 9 and 10, it has 2 different formulas for the sample size. One has a prior estimate, one does not. So let's see. It says he wishes to estimate proportion of Americans who own their home. If he wishes to estimate within 3% with 92% confidence. It doesn't sound like he has a prior estimate, right? So this is a no prior estimate. Okay, so we're going to use this formula. 0.25 times Z alpha over 2 divided by E squared. All right. And, okay, so what we're looking for, we have 2 things here that we need to find. Z alpha over 2 and E, but I think I actually might write E first. Let me put E first and then Z alpha over 2. Okay, so what is E? All right, well, E is, oh goodness. E is going to be your margin of error, right? So if you're estimating within a certain percentage, that's going to be your E. So E is equal to, remember, always convert your percentages to decimals, 0.03. Okay, and then the other thing is that it says we have 92% confidence, right? So my confidence level is 92%. Okay, well, if we're looking for Z alpha over 2, okay, if you look on a formula sheet, you're like, okay, cool, it says 90%, 95%, 98, 99%. And you're like, dang it, 92% isn't on there. Now on your final, it'll be one that's on the sheet. It's a common one, I promise. If you're in my class. Can't promise for everyone. But okay, 92%. So I'll show you how to do this just in case you're watching this and you're in somebody else's class and you are required to find this, right? Okay, so 92%, this means that, what is alpha, right? Alpha is the difference between 100% and your confidence level. So remember, that's the probability of making a type 1 error, is this alpha, right? So in this case, it's 8%. Okay, now, of course, we want to write this as 0.08 because we don't ever like to have percents. We like to have them as decimals. And I'll go ahead and write this as 0.92. Okay, so if we have alpha equals 0.08, then what is alpha divided by 2 equal? Because that's what it says, right? Z alpha over 2. So I need to figure out what is alpha divided by 2. Well, alpha divided by 2 is 0.04. Okay, so what I'm looking for is this number here, which I'm going to write it here, I guess. Z sub 0.04. That's what I'm looking for. Okay, now, how do we find that? That's the next question, right? So let me draw a little picture over here. So if you remember this notation, that if you have Z sub some number, that is the area above, right? So that means that this area right here that is 0.04. Okay, and then this number here is Z sub 0.04. Okay, that's what that is. That's what that notation means. That's what that picture is. So if I want to find this number, right, that's what I'm looking for, then I need to use inverse norm, just like we did on the previous problem. The problem is you have to know the area to the left, right, because this is area to the right. Inverse norm requires area to the left. So what's the area to the left? Well, oops. this area over here to the left is going to be 0.96, right? That's the area to the left. And then because we're talking about z-scores, your mean and standard deviation are just 0 and 1. Okay, so when we plug this into our calculator, inverse norm, I'm not going to show it because we just did it on the previous problem, but I do have to do it on my calculator. I get 1.75. Okay, so this is 1.75, and I think what I'm going to do is I'm going to change that to alpha over 2. Let me just write it over here. Okay, that's this number here. Okay, so now that we've gotten the, two things that we needed to go into our formula, we can just plug this into our formula, right? So hopefully I left enough space. I probably should have done that picture here, but I'm going to kind of partition off some space here in the middle. Okay, so n equals 0.25 times 1.75 divided by 0.03 squared. Okay. Again, I like to do this in multi-step, as a multi-step kind of problem. So I'm going to put this in on the next page, or sorry, in the calculator. So what was that? 1.75 divided by 0.03, enter, squared, enter. And then after we do that, there we go. Then we multiply it times 0.25, and I get 850.6, right? Now remember that it doesn't matter what comes after the decimal. The fact that you have something after the decimal means this is more than 850, right? Doesn't matter how much more, it is more, no matter what. Anything after the decimal means it's more than 850. It could be a very small amount more, it could be a large amount more. The point is, it's more than 850, and we always will round sample sizes up to the next whole number. Always round them up. So this is going to be 851 would be our sample size. Okay, so this video got a little bit long for me, so I think I'm going to go ahead and stop it here, and then I will do my next video starting on page 11.